Okay. So last time we saw two interesting data structures for doing range searching in higher dimensions. We saw KD trees, and we saw range trees. These things represent sort of trade-offs between query time and space storage. So we have sort of a space here, pre-processing time, which I'll just put in there, sort of related to the size of the data structure, and then query time. So for KD trees, these use order n space. They take only order n log n to pre-process, or order n log squared n if we're not too smart about how we do it. And then the query time is a little bit better than linear, but not huge amounts. So it's n to the 1 minus 1 over d plus log n plus k. All right, so that's the sort of first data structure we had. The other thing we looked at were range trees. And so these are a little bit bigger. So they take n to the log d minus 1n. All right, so in the case where d equals 1, these two actually reduce to the same thing, which is just a sorted list. Pre-processing, you can do it in n log d minus 1n time. I don't think we went into too many details about how that would work, but the idea is pretty simple. What you do is you first sort each of the points by their respective component, x, y, z, or whatever, store those indices, and then when you're building the subtrees, you can basically speed up finding whichever nodes need to be partitioned using that trick. All right, so that's kind of the idea there, right? So that reduces the complexity to basically just the size of the output. But more interestingly, we saw how we could use range trees to get n to the log d n plus k query time, which is exponentially better than what you get with a KD tree. So that's that. And so today we're going to look at basically two different things, which are actually more general ideas than just range searching, right? But we're going to look at them in particular as they would apply to improving these two data structures. So the first of these techniques is we're going to see how to take one of these data structures and then turn it into a dynamic data structure. And if you think about it, like with like a KD tree, right? It's kind of hard to think about how you might do like insertions into a KD tree or node removals, because you have this complicated sort of invariant where each node has to be splitting along some different plane. And so if we're deleting things or inserting things into the tree, preserving the balance of this KD tree becomes pretty tough, right? So if I delete like a node, then I have to find some new node that I can put in there and split it. And so that's kind of a mess, right? And range trees look even worse because we have all of these multiple levels of trees going into there. So I could probably figure out where to insert a node pretty easy, right? But if I do that over and over again, maybe the tree doesn't end up balanced at the end of the day, and I'm stuck with this horrible mess of a data structure, right? So instead of trying to figure out how to do each of these things efficiently for a particular data structure, using maybe some modification of a red-black tree or whatever, we're going to look at a generic solution that will take any reasonable tree-like data structure and make it dynamic automatically so that we can do insertions and removals with maybe some reasonable overhead, right? So the only sort of requirement here is that these data structures need to be relatively fast to construct, right? So we're going to basically use the fact that we can build these things pretty cheaply to basically get our constructions of insertions and deletions for free, right? So there are two techniques that we're going to see for doing this. They're both amortized, right? So these are not going to be sort of like constant log overhead type operations. Some of them may be very cheap and others may be very expensive. So it's not like a free lunch here, right? I mean, we're not going to basically be getting the same guaranteed log overhead that you would get with something like a red-black tree, but we'll get reasonable performance. So that's the goal for today. Or for the first half of this lecture. For the next half of this lecture, we're going to see how we can then take range trees in particular and speed them up a little bit. So we're going to be able to basically take this order log dn and kill an extra d on there, which will actually make them really, really fast in 2D and definitely speed up range searching in higher dimensions. And the rest of these things will be unchanged for the range tree. We're just going to drop this by 1, right? And that technique is, again, much more general than this and can be used for a variety of other things, but we'll come to that later. So, okay, first technique, dynamization, right? So this is a type of data structure augmentation. So it's sort of like a meta algorithm or like a higher order technique. We've already seen one of these, right, which was persistence. So we saw how we could use persistence to take any data structure and then turn it into one where we could travel backwards and forwards in time with it. Here we're going to show how we can take any reasonable static data structure and then turn it into a dynamic data structure with relatively low overhead. All right, so this is dynamization. And this is practically how you would implement these sorts of things, right? So there are two big approaches to this. The first one that we're going to look at is a technique called weight balancing. So how does this work and what does it mean? So, all right. This is basically a kind of augmentation. The idea is that we'll basically take a data structure with a cheap construction and allow fast incremental updates, while keeping the same query times more or less intact. All right, so that's kind of the idea. So it's sort of like, you don't have to mess with all this like horrible red-black tree stuff unless you're willing to unless you really need it to be de-amortized, right? But if you're willing to deal with amortized, this is much easier. So for this example, we're not going to look at KD trees or range trees. We're going to just start with something very simple, which is just a regular binary search tree. And once we see how it works for binary search trees, the extension to KD trees and range trees will be more or less the same. For this example, focus on binary search trees. Right? So just regular old, we'll just say 2D or 2-component binary search trees over a 1D array. Right? So, okay, let's draw a picture of a binary search tree. So remember, binary search trees, they just store sorted lists of elements, right? So we'll start with this list, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14. So it's 15 elements there, and we'll build a tree out of these things. So 7, 3, 1, 0, 2, 5, 4, 6, I guess 11, 9, 8, 10, and then 13, 12, 14. And we'll connect these things here. Okay. Right, so that's a binary search tree. No big deal, right? So, okay, suppose we have some arbitrary binary search tree, right? If I want to go insert an element into this tree, right? So suppose I want to add the node 15 to this list. This is actually not so hard to do, right? I could just walk through the tree, and if I don't care about keeping it balanced, right, I just figure out where the node 15 goes in here, which is right here, and stick it in the tree. Done, right? So insertions without having to worry about balance are trivial, right? So this is the first point. Insertions are easy if we don't care about balance, right? You just look for where the node has to go in the tree, right? Satisfying all other invariants of the tree other than the fact that the tree has to be, balanced on either side, and stick it wherever you want, right? So in a sense, if we didn't really have to worry too much about this, right, and our tree started from some state that was balanced, we could insert a node with basically order log n overhead, or in the case of a range tree, maybe order log d, or log to the d overhead, right? So in a KD tree, it would be sort of the same story. You could just walk down through the tree, figure out where the node has to go, stick it in there anywhere, right? And I could just keep doing this over and over again, right? So suppose I want to insert the value 10.5. Fortunately, all the markers are dying. So I can try this one. Suppose I want to insert the node 10.5. Oh dear. Yeah, if you have a colored marker, that would be great. All right. Small. Thanks. All right, so if I wanted to insert, say, like 10.5, oh, that's much nicer. I could just stick it right there. And I could just keep sticking nodes in here. So I could add another one for 16. That goes off there. Could maybe add in, I don't know, like 15.1, stick that there, and so on. The problem with doing this, though, is that if you keep running these sort of insertions, eventually this tree is going to get kind of lopsided, right? And in the extreme case, it'll just turn into a linked list, which is pretty bad, right? But if we only do a small number of insertions, right, so we've only just done a tiny amount of modification to the tree, then the tree is actually pretty close to balanced, right? And so if we only do a tiny number of insertions, then the total change in the height of this tree is going to be relatively tiny, and so it'll still be mostly balanced. And so we don't have to worry too much about small numbers of insertions. It's just that after we get too many of them, then things start to get bad. All right, so that's the first point. So insertions may not be so terrible if we don't care about balance. If we do care about balance, then we have to do something about these cases when it starts getting horrible. The second case is that if we wanted to delete a node from one of these trees, right, then here's an easy way that we could do it. We could just store a flag on each node that says alive or dead. And if we want to delete something, then we can just set the flag to dead. And so we'll just have like a little hole in our data structure, but the rest of it will still be intact. And as long as we don't have too many holes, things aren't going to be too slow, and we can still do all of our normal tree operations. So we'll just say deletions are easy. If we just flag nodes dead or alive, right? So for example, suppose I want to delete the node 3, right, from this tree. All I have to do is just mark this guy dead in the tree. And then whenever I do a search, I'll still search on the node 3, right? But it's just when I'm querying results, I don't report 3, right? So basically all that dead means is that the node is still in the tree. It's still there for using all of the other sort of operations that you'd want to do with this node. It's just that if you're going to be querying the tree and you want to report all of the results within some range, you skip any dead nodes. That's the rule. And so if you only have like maybe a constant number of dead nodes, this isn't going to be a big deal, right? Because again, the tree will for the most part be fairly well balanced, right? And the number of these dead nodes is going to be fairly tiny. And so in any interval, you're not going to have too many dead nodes that you have to worry about when you do a search. So as long as like the number of dead nodes in the tree is maybe some constant fraction of the total number of nodes in the tree, we would be OK, right? So that's the idea, right? Is that we're going to basically do insertions and deletions like this using these sort of like lazy, crappy tree updates, right? And so the tree is going to get a little bit messy and broken over here, right? But we're going to do a couple of things to fix it up, all right? So that's the idea. So the key, though, is that we need to figure out when we need to do one of these fix-ups, right? So we basically want to keep doing these insertions and deletions and like messing things up in the tree, but we're only going to do some fix-up to this tree when things start to get like really out of hand and like broken, all right? So that's the idea. So, OK, so how do we define this sort of concept of a somewhat fuzzy or broken tree, or how do we measure the sloppiness of one of these trees? So here's how we're going to do it. Right. So we're going to need to define a pair of measurements for one of these trees, which should be pretty straightforward. So, OK, where will I write this? I'm going to write it right here. So here are two parameters. Right? It should be easy to think about how you would define this. First is we're going to define the size of a node in a tree. This is just the total number of live nodes in the subtree. All right, so if I take, for example, the subtree rooted at 7, then the total number of live nodes here is going to be, I guess, so we have 1, 2, 3, 4 live nodes over there, plus the 15 here, minus 1, so it should be 18, right? Or if I take this subtree rooted at 3, the total number of live nodes is 6, because it would normally be 7. However, 3 is dead, right? So that's the idea. So we're basically just going to count the total number of nodes in a subtree, right? If we think back to last time how we were talking about these dyadic intervals, right? If I take any node in this tree, it spans some interval inside this range, right? So we're just going to think of this as just count the number of nodes in the tree rooted at some node, right? That's the size of one of these things. But we don't count the dead nodes. So the other measurement that we're going to have is we're going to have another measure where we count the size of the tree plus all of the dead nodes that happen to be contained inside there. And we're going to call this max size. So this is basically the size of tree are the number of all nodes, basically the descendants of node plus node, right? So we're basically going to just take one of these nodes and then count the total number of nodes in it. So for this tree here rooted at 3, the max nodes of this tree is 7, and the size of the tree is 6. Our max size is 7, size is 6, right, for that particular node. So hopefully that's clear, right? So we have basically this one that counts like the total amount of stuff, right, that we've allocated in the data structure, and the other one is the amount of stuff that we're using. All right. So what we would like to do is basically put some constraints on these size and max size values, right? So for a strictly balanced binary tree, we have the following constraints. And I'm going to erase some stuff here. Yeah. All right. I'll just write it like this. So we have two sort of equations in a binary search tree that we have to obey. The first is this, that if we take any child of a node, so the size of node.child, I guess this could just be like the left or the right node, however you want to write it. This has to be equal to at most 1/2 of the size of the node. So I can actually write it as basically less than or equal to 1/2 times the size of the node, because they can always be imbalanced by a factor of plus or minus 1, depending on if the tree is full. Right? And so this is the basic property that ensures that the height of this tree, right, is at most log n, because if you have 2 children here, then each of them has to basically cut this into 2 pieces. Since we know that size of node can be written as basically like the sum of the size of all the children plus 1, right? So if you basically sum up all of the children's sizes and add 1, then you get the size of the node. Here, I guess we're only worrying about the case where we have 2 children, right? So it would basically just be 1/2 of that. So by the pigeonhole principle, these 2 nodes have to be basically the same size, right? They can at most have plus minus 1 difference in their size. The second one is in a strictly balanced tree. We have no holes in it, so we basically set, I'm going to write it like this. We set the size of a node exactly equal to the max size of the node. All right, so these are sort of the strict equations, right, that we would have to satisfy for like a perfectly balanced binary search tree. All right. I'm going to erase that little equation there. All right. So what we're going to do is we're going to introduce this extra parameter, which we'll call alpha. which measures the amount of sloppiness in this tree, right? So we're going to add a new parameter, and we're going to modify these constraints on the tree a little bit, right? So we're going to basically introduce alpha, and this thing is going to be between 0 and 1, non-inclusive. So it better be somewhere bigger than 0, but definitely less than 1, right? So this is an open interval. Alpha 0 less than 1. This measures sloppiness. Or just how much of this kind of, violation of these two constraints that we can have. And so the way that alpha is going to show up here is that we're going to modify these two equations a little bit. Right, so how do I want to write this? Yeah. So the first one here, what we're going to do is instead of allowing it to be 1 over 2 for a binary tree, we're going to be 1 plus alpha over 2. And then this one is going to be 1 minus alpha. Right? Yeah. And we're going to modify this here so that it is less than or equal to 1 minus alpha. So these are the new constraints that our new weight balance tree is going to have to satisfy. So these are the weight balance conditions. Okay. So let's think about this for a moment. So what happens if we pick alpha equals 0? Well, in the case where alpha equals 0, this will just degenerate to the strict conditions, right? So that's OK. What happens if alpha equals 1? Well, if alpha is equal to 1, then pretty much any crazy data structure that we would basically have over here in any weird state would be valid, right? So what happens if we pick a value of alpha somewhere between these two extremes? So to basically summarize that, right, we'll say alpha equals 0 implies balanced BST. Alpha equal 1. I guess you could just think of this as like a linked list, but it's actually even crazier because you can actually have holes in the list, right? So it's just like some weird mess of a linked list data structure, just any old crazy thing, right? So alpha equals 1/2, question mark, question mark. What do we get? I don't know. Well, that's actually the data structure that we're going to build, is we're going to pick alpha equal 1/2, right, in practice. Or you could pick any other value, but 1/2 is good enough, really. Like, it doesn't need to be anything different than that. So we're going to pick alpha equal 1/2 for today, right? So, OK, so let's think about this, right? So first of all, if we know alpha is equal to 1/2, let's try to work out the size of the tree, right? Well, we actually know something about that, right? Because if alpha is equal to 1/2, right, then we can actually figure out what max size is as a function of size, right? That's the trick. So how does this work, right? So here, I'm running out of space. I'm going to have to erase some things. I guess I'm just going to have to erase this tree, which is unfortunate because I wanted to kind of refer to it. Yeah. Yeah, I could erase some of this stuff here. All right. All right. We'll put it in this spot here. So it's a little messy, but we'll kind of deal with it. So, OK. What happens to max size and size, right? So, OK. All right, so we first know this, that basically size of node is definitely less than or equal to max size. Right? Because we have to at least insert the nodes before we can delete them in some subtree, right? So that's a fact. And we also know oops, I wrote this. This has to go the other way. That's where the mistake was, right. So this has to be bigger than 1 minus alpha times max size, not less than or equal to that. Sorry about that. Okay? But we now have a lower bound here, right, which is that 1 minus alpha times max size is less than or equal to size. All right? So this means that in the worst case, right, assuming that the number of nodes that we have that are alive in the tree is n, the total number of nodes in the tree can be at most n over 1 minus alpha. So for tree with n items, so this is sort of what this implies, with n items, max size is at most n over 1 minus alpha. Right? That's the conclusion from that first statement over there. So draw this whole thing in a box.
Something still seems a little weird because you're saying that half of max size is less than equal to size of node, but max size is also greater than equal to size of node.
Yeah. So it just means this has to be between this thing, right? So it just means that it's within this space over here, right? Or another way to think about that is if we pick alpha equal 1/2, the total number of nodes in this tree is going to be at most 2n, right? Yeah. So we never get more than 2n extra nodes kind of sitting around in here with all these like dead things that we've blown up, right? Assuming that we keep this invariant, right? That's the trick. So, okay?
Yeah, okay.
All right, so this just means that the tree never gets too large if we enforce this thing, right? It'll always stay order n, right? Or basically, tree is still order n. Order n tree. So we basically don't have a substantial growth in our data structure from doing all these deletions and leaving holes all over the place, which is good. All right. Okay, next question is what happens to the height of this tree if we have to enforce this relaxed balance constraint, all right? So if we have to basically think about what's going on with that, and again, I run out of space. I guess I'll just write it over on this side. I don't think we need to see these anymore. Right. So think about what the definition for the height is, right? The height of a node is going to be 1 plus the max of the height of either of its children. So we just, do this over all node dot child, I, whatever. So you just, for every child of this node, we take the max of all of their heights, and then we add 1 to it, all right? Now, another way we could also think about this, right, is that if we parameterize this instead of being as a function of node, right, we're going to think of this as now a function of n, the number of nodes in the tree, right? So we'll write this as basically our number of items in the tree, order n here. So this is going to be the max of this height plus the height of, the size of node child I, right? But from this equation, we can rewrite this as height of n, right? And if we take the max of all of them, it can never be bigger than this quantity here, right? So this is going to be height of n plus 1 times the height of 1 plus alpha over 2n, right? So that's just translating that sort of invariant using this idea here, right? So we're now rewriting this not as a function of a node, but now as a function of the number of elements in the subtree at that node, right? Which is what we want to get. So how much is that? Well, if this parameter here, right, happens to be less than 1, which is true for any alpha between 0 and 1 inclusive, right, then this is going to continuously decrease, right? We're going to basically be cutting it down by a fraction of maybe in the case where alpha was 0, we cut it down by a fraction of 1 over 2, and that gives us a tree with log 2n levels. Or if we're cutting it down by some other parameter, say 3 over 4, we'll have a tree with log 3 over 4 levels. In general, this will give us a tree with height of n equal to order log 2 over 1 plus alpha n levels, right? Or in the case of alpha equal 1 over 2, this will give us log 4 over 3 n levels in the tree, right? So what this means, right, is that if we enforce these two, is that if we enforce this condition, right, combined with this condition that makes the tree not get too large, right, then we'll be guaranteed that we're still going to be having roughly logarithmic query time, right? I mean, or it will be logarithmic, not roughly. I shouldn't say that, right? It will still be log query time because the height of the tree is basically the bound that we have on any query that we have to run on the tree, right? There are always just going to be some traversal of a root to leaf path, which is just height of n, right? And that's at most log n, all right? So, okay. Right, now this also points out why we need to have these different values of alpha, right? If we take alpha equal to 1, right, this actually will blow up, right? And our query time will actually be order n because we're taking like log 1n and it'll just do something weird. Similarly, this can just become unbounded, right, when we pick n over 0. So this actually goes to infinity, right, in the case over there where we could actually just keep deleting nodes indefinitely. So that's why we have to make sure that we have this constraint here. It has to be an open interval. We can't allow the two endpoints in order for this to really work out, right? Actually, no, alpha equals 0 would be valid in these equations, but alpha equals 1 definitely will blow them up, right? So we can't allow alpha equals 1 for these two things to still be valid. All right. But we'll see why we need the alpha equals 0 when we go to the analysis of this later. So, OK. Now we've seen that if we can maintain these invariants, that life will be easy, right? Or at least we still will have a usable binary search tree data structure, as long as we can enforce weight balance, right? So how do we do that under these insertions? The answer is really simple, all right? Here's what you do. You just keep inserting and doing this other crazy stuff however you want, right? And if ever you get to a condition where these two things are invalidated, what you do is you just back up the tree to whatever ancestor at which this constraint was like broken, all right? And you just blow it up and rebuild that entire tree from scratch, right? That's all you do, all right? It's very, very simple. So for example, if I just keep deleting from here, eventually this whole tree becomes unbalanced. I'll just have to go through, blow that whole tree up, and then rebuild it from scratch using my tree construction procedure. And now I have a nice, perfectly balanced binary search tree that I can then run all my queries on, right? Yeah. So let me kind of go through why that actually makes sense, or what's the cost over here, or try to figure out how I'm going to write things. I guess I'm just going to erase this stuff here. Hopefully it won't turn out that I need this. But OK, so here's sort of the idea. I'll just walk through one step of that. Just suppose I just keep deleting nodes here. So I delete this thing, and then maybe I delete this thing. Now this tree is unbalanced. So what I'll do is just blow it up and replace it with a tree that just contains 0, right? Or if I keep inserting into the tree, -1, -2, etc., at some point it will become unbalanced. Then I blow that whole thing up, make a brand new tree, right, and just stick it right there, just using my ordinary tree construction procedure. All right, so that would then be whatever, something. I don't remember what things I wrote down there, but that's OK. So this is the idea, right? Insert and delete using obvious method. If weight balance is violated, rebuild largest broken subtree. That's it. Very simple idea. The way you would do this in a KD tree is kind of self-evident. You just do the inserts and deletes exactly as the KD tree invariants would expect you to do, ignoring the balance constraint. Once you break weight balance inside your KD tree, rebuild. You can do the same thing with range trees, right? Because it's pretty easy to insert into a range tree. You just walk down, insert the node into whatever node of the range tree you want to put it in. and then also through all associated subtrees, right, which is basically going to be the cost of locating the point in the range tree, which is, again, basically like log squared n. And once you've done that, right, you basically, again, check this weight balance constraint. If it's broken, rebuild that whole chunk of the range tree, or rebuild whatever associated tree is broken. You just nuke it, build a new one, right? Easy. Same story with deletes. If you basically find that at some point you violated that constraint that I just erased on the max size, rebuild, right? So why does this work, right? Well, one way to think about this is that every time we insert into the tree, we can basically charge some of this construction to the insertion itself, right? And so here's the point, is that we'll only have to rebuild a tree after we've done at least order, the size of this tree that we're rebuilding insertions, right? So let's call the size of this tree S, right? So only do order S rebuild after alpha S, or after 1 minus alpha S, I guess, right? Is that right? No, I don't know. No, after S over alpha, right? Rebuilds, right? No, is that? No, it's, yeah. No, alpha times S, right? Alpha times S modifications. Right. Yeah, so we only have to rebuild it after alpha times S operations. That's the key thing that makes this all work, right? Whether they're insertions or deletes or whatever. So we can basically think of this S here, in the worst case, as actually being n, right? Because we're only going to be basically changing n with each of these things. And so if we think of it in this way, right, then we'll have to do one rebuild per level of the tree in the worst case, right? So there's an extra like log overhead on here. So the total cost, right, is basically cost of rebuild, which we'll write as like C for construction. So we have C of n divided by alpha, but instead of S, we're just going to put n in there because n is in, or S is in order n, times log n per operation, right, per update. So that's the cost of doing one of these modifications to your tree, right? So you can see now why we have to pick alpha greater than 0, right? So because if we picked alpha equal to 0, you actually have to rebuild every single time, and then this just becomes like an enormous cost, right? Because you can't actually do it. But if we pick alpha equal to 1/2, then this just becomes construction cost of n, of rebuilding a subtree or whatever, divided by n times log n, right? So for a KD tree, this gives us updates in log squared n amortized. For range trees, we get updates in log dn amortized, which is relatively good. So that's the first way that we can build a dynamic data structure. Take any one of these sort of tree-like data structures where we have this hierarchy of trees that can easily be rebuilt, and then just make it dynamic. Right? So any questions about that or any comments?
I thought it didn't add any extra factor for binary search trees to the normal one, but maybe I'm just wrong.
I think it does because you can have to like basically keep doing the rebuild over and over again, so you end up having to like keep repaying it. So you have to charge for each of the trees along this root to leaf path, right? So that's why I think you have this extra log factor in there. But maybe I'm mistaken. I don't know. I'm pretty sure you need that extra log factor actually, but I may have to double check that. I don't know. I worked it out this morning, and I came up with an extra log factor, so that's what I got right now, right? But maybe I made a mistake. All right. OK, there's another way to do this, though. All right. The other way is that you can also use a technique called log-structured merging, right? Which is kind of the same idea. And you can get rid of that log factor in some cases when you have a nice merge operation for your trees, right? So if your trees were like sorted lists or something, then you can kill that log factor. But for general range trees or KD trees, it doesn't really get rid of it because merging is kind of complicated and hard, not so efficient. So, OK. Yeah. So I won't spend as much time on this one because it's kind of a simpler idea. And also the details get a little bit messier to kind of write out. So I'll do it more superficially. But this is a technique that's used a lot in databases. So like LevelDB uses this idea. A lot of file systems use this same technique. So this is just log structured merging. And so the idea is that instead of having just one tree for our data structure, we're going to have a forest of trees, right? And they're all going to be of different sizes, basically some power of 2. And they'll either be filled or at most half empty. Right? So there will be at least half of the 2 to the n nodes in there. So we basically we have a forest of trees Ti with I guess we'll say Ti is either is empty. So either like one of these trees is going to be just like completely empty, like not filled at all, or the size of Ti is going to be between 2 to the I and I guess 2 to the I plus 1, something like that. All right. So we have basically like this sort of ascending set of trees, right? So how does this work? Again, for deletions, we'll use the same trick. Well, so let me first say how we do searches, right? Because that's actually kind of important. So for searches, run same query on all trees in parallel, and then just merge the results. So if we're doing like a range query, we just run it on T0, T1, T, etc. And because each of these trees is relatively small, the total size of the trees is order n. So we've basically, we've just basically used the sort of geometric series trick, right? To basically put at most a factor of 2 in front of our constant over here to run this thing, because each of these trees gets smaller, right? So assuming that we have like say log size query or whatever, it's fine. So okay. Second trick here. Right, is we'll say delete. We'll basically just use that same technique that we did last time, where we'll just flag nodes as dead inside a tree. So they'll just poke a hole in one of the trees or something like that, and then we'll still have like the node in there. And inserts will create a new tree. Or in practice, the way you would actually do this is like the lowest level of tree would just be like an unordered list of points, right? And you could just scan through it, typically, right? So we'll just have this sort of like pool of trees that are just, or pool of points that haven't been allocated into a tree, which will be of constant size, right? So the lowest level trees, you wouldn't even bother with the data structure. You just have like some little, set of floating points. And so here's the idea, right? So if we delete a tree so that it becomes a node from a tree so that it becomes smaller than this value, right? Then what we do is we take that whole tree and then all of the other trees which happen to be smaller than it up to some size, merge them all together and build a new tree and then stick it in the list, right? So we'll just blow that whole tree up, right? And we'll rebuild it, and that's fine, right? That's only going to happen after we've done 2 to the I of these operations, so it's pretty rare, right? The smaller trees will get rebuilt more frequently, but that's OK, right? Because they're smaller. Right? When we insert a new point into here, right, then it basically becomes something like that increment to binary counter game, where what we do is we just scoop up all of the trees which are already filled up to some level, right, merge all of those things back together and build a new tree, right, and then just keep iterating that process. So hopefully that's the idea. So we basically use the sort of binary counter amortization type argument to just merge filled trees, right, and split empty trees. So we basically just say, after any update, merge r/split empty trees. That's basically it, right? So you just go through, look for any tree that's overflowed, right? If you have like 2 extra 1 trees together, you just merge them all together to build a tree that's sufficiently large. And if you have any tree that's underflowed, then you just split it apart, right? And that's basically it. So pretty simple idea. The cost of this, well, basically we only have to do one of these rebuilds of a tree of size 2 to the I after about 1/2 to the I updates, right? So we're still basically doing amortization within the same overall regime as before, right? It's going to be cost of construction divided by the number of operations that we've done on the tree. So it gives you similar performance, but the nice thing with this is that this can be a little bit easier to implement for trees that don't happen to be tree-like data structures for arrays. And the other thing is that because we're actually starting from a tree here, you can use maybe some sort of merging technique to speed it up in practice. So if these were all sort of like sorted lists, this is a really nice way to maintain a bunch of sorted lists on, a database, right? So LevelDB uses things like this to basically implement, like dynamic data structures relatively fast, right? So this is kind of like people use in real industrial systems that have to have like really fast range queries, typically like databases. You can do the same thing for range trees, right? It's kind of obvious how you do that. Same idea. I don't think there's much else that I want to really say about it at this point because we need to move on to the next thing, which is how we get that extra log factor out of our range queries.
So what's the complexity of the log structure merging?
If you don't have a fast merge algorithm, exactly the same as the last time. So it's cost of construction divided by n times log n, right? Ignoring the alpha parameter there, but it's basically the same result.
And for range trees and KD trees, do we have a fast merge, really?
Not really. All right, not that I know of. Right? There's no really fast merge, right? So you can just do this technique, and it would basically get you back to the same thing. I mean, there are algorithms for merging KD trees, but they're really complicated, and I don't know that they're terribly useful. Similarly for like range trees. And actually, an open question is that both of these results are still amortized, so while you get relatively fast updates for most cases, you're still going to have this sort of like problem where if you've charged a bunch to the data structure but haven't paid it off, then eventually a really big merge is going to come by and hit you and like wipe you out, right? So for real-time applications, like maybe like something in like finance or something, I don't know, they may not be suitable, right? So you'd have to worry about like maybe some way you could de-amortize that. I don't actually know of any good results for how to de-amortize these types of operations, but it's an interesting kind of idea to think about. So yeah, that would be kind of cool. If someone could figure out a way to do automatic dynamization without this amortization business, that would be really interesting.
There have been like some results for like dynamic KD trees.
Yeah, there are dynamic KD trees, right? But they're really kind of messy. And the dynamic KD trees, there are also dynamic results for range trees, but they're sort of in the same like red-black tree type regime, right, where you just have this sort of like really weird tree rebalancing rule. It's not as easy, right? But yeah, I don't really know of a good way to do de-amortized dynamic data structures like automatically like that. But yeah, that'd be kind of neat to look at, maybe. I don't know, or maybe it's not possible. I don't know. Who knows, right? Anyway, I need to talk about the next thing, which is fractional cascading. And my marker died. All right.
What?
Yes.
Might have to be green.
No, that'll be fine.
Okay. Christmas colors.
Yes. It's very festive.
Tis the season.
All right. Fractional cascading. This is how you make range searching really, really fast for range trees in 2D at least. So for 2D orthogonal range searching, what we'll see soon is kind of the state-of-the-art optimal solution for doing it. But this idea here, fractional cascading, by itself is actually a little more general than that, right? So it's actually a technique which you can use for a variety of different things. It can be applied in some sort of generic setting. So we'll talk about the basic idea, right? It's in some sense independent of range searching, but the context in which it was first discovered was range searching specifically. And here's the basic idea, which is we have k lists, right? So we'll just say given k lists, we want to maybe pre-process them or do something so that we can speed up binary searches with the same value, right? So we want to basically pre-process so that we can efficiently search them simultaneously. Right? So what I mean is that we're going to have a bunch of these lists, and we're going to pick some fixed value, and we're going to just rerun the search to locate, the predecessor and successor of that value in each list, maybe in parallel. So to get things started, we'll just draw a couple of lists here as an example. Actually, I'm going to want to leave some space between these numbers. Maybe -10, 10, 20. Maybe that one only has 3 values in it. 5, 6, 8, 100, -1, or right, -2 becomes 3, 0. Right. So we have these lists here, right? And what we want to do is take some value and then find it in every one of these lists. So maybe our value happens to be, say, 7, right? So if I take 7, I'll locate it here, right? This value would then end up being here in this list, then here in this list, and then maybe here in this list. So we want to just do a bunch of these binary searches, in parallel, right? So that's the high-level idea. Yeah. Actually, I maybe picked kind of a poor example to get started with this. So I'm going to erase this row here, do something a little bit kind of post hoc. Right. Let's go set this to, say, 0.5, 0.7, 4, and 6, right? I don't know, whatever. So that's the idea. So, okay, the naive solution, right, is we just take every one of these lists, we sort them, right, and then we run k binary searches in parallel. So the naive solution sort each list, run k searches. And the cost of doing this is order k log n, right, where n is the size of one of these lists. So we'll assume that they're all roughly like the same size, or that we have order n elements total, right? So that's, okay, not a big deal, right? If k happens to be pretty small, this might not be so bad, right? So if we only have like maybe 1 or 2 lists, perhaps this is a reasonable solution. The problem, though, is what happens if k is big. Say k is on the order of like square root of n, right, which could reasonably happen. So we have like a huge number of lists, right? Well, in that case, then this is going to be kind of terrible, right? So imagine if we had like a really big list chopped up into like a bunch of like tiny little pieces, then this is not going to be too quick, right? So an alternative solution, right, is that we can just merge all of the lists into one big list, right? So, and then we'll just keep track of their, index within each sublist, right? So basically, for each of these things, we're going to figure out where the element is located, right, in each of these lists in parallel, right? So for 0, we'll say, okay, 0 is stored at, coordinate 0, 0, 0 in all lists. This is stored at index 1, I guess index 1 here. no, actually 0 is not stored at 0 down here. It's actually stored at 0, 1, 2, something like that. So just for every element, we'll just store where its indices are in all lists, right? So 1 is going to be then stored in 1. Maybe it'll actually come after 0. Something like that. I don't know. 1, 0, 2, something like that, right? So we basically go through for each element in this thing. We run the binary search on each of these other lists. We store where the element happens to be located in each separate list, right? And then merge all the lists together and sort them. Then we can just do one binary search on that big list, which will take time order log n, and then report each of the indices. So we can basically merge them together. Merge lists together, store pointers. And the time complexity of doing this, right, will basically be order k plus log n, because we just have to do k lookups and then one search, right, which will definitely be faster there. But this uses order k times n space. And so if k was pretty big, this would actually be kind of bad again, right, because we're going to basically be storing a ton of extra space in order to manage all of this, right? So that's not a great solution. So what fractional cascading does is it gives us a way that we can basically get the best of both worlds. We'll get this time complexity for running our query, but with merely order n space. So this one, we should point out, uses simply order n space. It's very compact, right? And then this, will basically be pretty fast. So we get both in one, right? And then we'll see after we've done this how we can use this technique to speed up range searching through a technique called layered range trees. So that's the idea. And so fractional cascading is actually a combination of two ideas, right? The first is called cascading, and the second one is called the fractional, right? It's the fractional part. We'll talk about that in a moment, but let's talk about cascading now. All right, cascading is actually a really simple idea, right? We already saw kind of how this worked, which is that if we're doing these successive binary searches, we can speed them up by basically using where we've located an item in one array to then locate it in the next array, right? How do we do that? Well, we have each element here store a pointer to its position in the other array. So it stores like a pointer to where it would be located, so its predecessor and successor in that. So 0 will basically store a pointer here. 1 would store a pointer here. 2 stores a pointer here. 3 also. 4 there. Right? This would go here, there, and maybe this goes here, right? Similarly, 5 now goes here. Right. So that's the idea. So if I want to do a search now, like I take an element, say, like 2.5, well, I first do log n work to locate it in the top array. Then I can use the pointers to speed up, right? So I then basically go here. Well, I know it's 2.5, so I only have to search in this range. Now I've found it there, right? Now I can then take the fact that I know it was there and locate it here, then use that and locate it. Well, because it's actually in the range, then I have to do a whole binary search over this last range. So in some cases, it seems like cascading can speed up things quite a bit. But in this last case here, if you look, I have this enormous range. Well, that didn't really help me that much, right? So I still have to do another log n work on that list. OK, but in some cases, right, if these lists were all sort of uniformly distributed, right, so if each of these elements was uniformly spaced in each list above it, then this cascade would basically allow me to continually look forward, going to the next list and then locating where I am in that thing. Just keep doing that, right? So it's basically, so cascading. I'll define how this works. So we just, we store pointers to index in next list. So basically, we store our predecessor, successor value for each element, and then we can use that to speed up range queries. All right. The main insight here is that if lists are uniformly be distributed, or basically if they're all sort of within the same set of values, the similar kinds of ranges, they all fit together, so that each of these little ranges are pretty small, this is going to basically speed it up enormously, right? But the problem, though, is that you'd say it could be fast, right? This is not a very strong thing. There's sort of an intuitive statement, right? This is kind of the idea, right? So you can imagine that this cascading in some case might give you a very big benefit, right? So the question then is, how do we get to a case where we can use this cascading and actually speed things up? And this is the fractional part of fractional cascading. And so here's the idea, which is that what we're going to do is we'll take each of these lists here at the bottom, and then we're going to propagate up half of the elements in that list to the list above it. And we'll just store them as sort of dummy elements in that linked list. And then when we do the search, we can then just walk to the correct element. So let's do that. I'm going to build a brand new data structure here. Actually, we'll keep these pointers intact. OK, so what I'm now going to do is I'll add these new elements here, which I guess they're going to be negative. I wish I had another color. I'm going to try one of these black markers. Maybe I can get one that'll work. Yeah, that one looks OK. So here's what I'll do. I'll store these elements here, -3, -2, 0, 3. And then I guess 7 goes there. All right, and then these are all going to store their own sort of pointers to themselves. Right? And now I'll just... Yeah. Actually, and then there's one other thing I forgot to say here, too, which is that we only want to propagate half of them. So I did this wrong, actually. I did a slight mistake. Right. Well, you'll see why, right, in a moment. This is why it has to be a fraction, and why it's called fractional cascading, not just cascading with everything all smushed together. Because it turns out if we did that, we would actually end up doing this thing, right, which is just merging them all together.
I guess, OK. So I was thinking you would only take half of the actual list to propagate up. Or, sorry, take the whole list to propagate up, but not half of the previous elements.
No, we take half of this list. So we're going to put -3, 0, and then 7. So the way we do it is we take every other element in this sorted list down here, and then stick it in the list above it. Now we do that here. So we take every other element. So we take -3, put that here. 5 goes here. 7, which goes here, and then 100. All right. I'm just going to erase the pointers, and I'll redraw them. All right, and then we repeat it again with the list on the bottom. So I'll end up with -3 here, 1.7, 5, and then 7. All right? And then now here we can go store our pointers. So 3 will point down there. Similarly, 0, I guess point here. I guess, yeah. Yeah, 0 points there. Right. 1.7 points there. Yeah. OK. And then 3 goes here. 6, 7, 100. 0 will go here. All right. Now here's the trick, right? So we have a lot more pointers over here, but this is the neat idea, right? Which is that first of all, let me say what I just did here. So the fractional part. Or I'll just call it fractioning. I don't know. I just made that word up. is we basically propagate 1/2 of all values to previous array, starting from bottom. All right. And so what this will do, right, is if we run a binary search, right, on the top level of the array, so suppose we want to look up the value, I don't know, let's try 2.5 again. So we try 2.5. Again, we do log work on the first one over here, which is the size of this whole array, right? Locate it here. Then we can use a pointer to immediately locate it in the next array. And then because these elements are now uniformly mixed with all the other elements over here, we're guaranteed that we're always going to land within 1 unit of the array below it, right? So the way that we can think about it is that for every node in this array, there's now at least one pointer going into it or one of its neighbors, right? So that the pointers are now uniformly covering this array, and so the amount of work that we have to do for each subsequent binary search is at most constant, because each array, or each interval for each sub-array is going to be of a size which is proportional to how big we picked this fraction, right? So the fractional part of fractional cascading just constrains the size of these intervals that this cascade determines for each successive level, right? And so when we combine these two things together, let's look at it, right? Well, our new time complexity is we have to do one search on the first list. This list is going to be at most order n, right? And so the cost of doing the first search is log n. And then for each subsequent level, we only have to do constant work. So we have k extra steps. So the cost of doing a query in fractional cascading is order k plus log n, which is as good as this insane algorithm over here. Now, how much space does fractional cascading use? So if we think about this in terms of space, well, we basically added half here, right? Then we have half of the bottom array plus half of the first array over here, right? Or no, a quarter of the bottom array plus half of this array gets propagated up, then an eighth of the bottom array, and so on. So we have sort of this geometric series. So each array gets increased by a factor of n plus 1 over 2n plus 1 over 4n, etc., which is at most 2 times n, right? So the space complexity here is at most order 2n, right? Or order n space. So that's here. So we get the best of both worlds, right? That's the idea. So we can basically use this to answer this repeated binary search problem in both, fast query time and efficient space. That's what fractional cascading is all about. All right. So now, with the remaining time, I will say how this now applies to range trees, right? And in particular, I will talk about how it applies to 2D range trees. Because the way that you would actually use this in practice is that you basically would say, okay, you'll do a normal range tree for all of the higher dimensions, and once you get down to a 2D range tree, you will use this trick, right? That I'll now sketch out. All right. So is everyone okay with this, though? Does this make sense? Any questions about this? Does it seem confusing or straightforward or maybe undecided? I don't know. OK. I'm going to erase it. All right. So people have probably seen that before. Here's the next step, though. We have to mix this with range trees. So these are right. And that stuff you can find in debug, right? So you can just look it up in a book. It's kind of covered there. So, all right. So we're going to now add in range trees to the mix. And the result is called a layered range tree. And it's pretty much the same idea as we already saw for range trees, except we're just going to use fractional cascading to speed up the search on the last level of the range tree. So it's sufficient to explain how this would work for just a 2D range tree. All right? So we'll say given a 2D range tree. So I'll sort of draw a picture of it here. So imagine this is sort of the x component. So we'll basically store x component as usual in a sort of standard binary tree. And then for the associated data structure, we're going to use arrays, right? So for associated y data structure, use arrays. So here's sort of the picture. So we'll have some element here. This is our associated array. Actually, let me draw these arcs in a different color. Right, so just so it doesn't get too confusing. So we'll say we have a couple more arrays like this, and some arrays on the bottom. Something like that, right? And each of these little trees here is going to be having a pointer to their y array, etc. And then we have pointers going here and here. All right, it looks kind of messy, but it's hard to draw this thing on a blackboard, right? So this is sort of our X tree. And then this is basically the Y arrays. And so here's what we'll do, right? If we look at what happens when we run one of these range searches, let's imagine that instead of waiting until we've already located a complete subtree, we start the Y range search immediately, right? Then if you think about what's going on here, we're starting with our X range, right? We search through this tree. We're going to find these subtrees and then run the binary search on Y. But what if we jumpstart our binary search on Y up here, right? So we first start searching on X, and then we start searching on Y. And then we just rerun these binary searches on Y over and over again. Well, this is exactly the problem that we had to just deal with fractional cascading, right? Where we have basically our initial Y range search here, and then we have to basically propagate it down here. So what we're going to do is store a pair of cascades for each of these levels of the Y range tree. So each of these nodes is going to have a pointer here and a pointer here to wherever it ends up in each subtree. And then we basically use cascading on Y tree, run Y range query in parallel to X. Well, what does this give us? Well, first, to get this whole thing started, we have to do order log n work on the top level of the Y array over here in order to get the start for the Y cascade, right? And then after we have that, each subsequent step on this Y tree is constant. And so we can amortize each of those steps over a traversal of the X tree. So the traversal of the X tree takes order log n time. Bootstrapping Y here takes log n time. And so the total cost of doing this is only order log n instead of log squared, right? So this reduces query time so we go from order log squared n plus k to order log n plus k, which is actually really good, right? That's actually a very big speed up in practice. And so if you want to really do 2D range searching as fast as possible, this is pretty much like the best in breed data structure for solving this type of thing, both in theory and in practice. In higher dimensions, the problem with range searching using range trees is that the trees just become enormous, right? So that kind of defeats them. But actually, plenty of databases actually use this technique, for implementing 2D range queries. So like Redis, right, which is a fairly popular database store, uses layered range trees to do 2D range queries, right? Because it's just faster than any other data structure for doing that. And so that's kind of the idea, right? So fractional cascading is a net win, a pretty good idea to do that. Of course, it still is only really like fantastic in 2D because the storage costs of higher dimensional range trees get to be a big deal. If we combine this with the rest of range trees, this actually reduces the total cost of a range search in general from being log dn to being log d minus 1, right? So generally, this gives us order log d minus 1 n plus k queries, right? You can reduce this further to log d minus 2 for 3D, which is actually a very, very complicated technique. And we're not going to cover it in this class because it's just really, really insane. Right? I would probably spend like a whole lecture just talking about how to shave like another log factor off of this exponent in 3D. And it's even then still not totally practical because you have a very large space complexity associated with it. But theoretically, it's possible to get to log d minus 2 in general. It's an open question if you can actually do log n plus k in general for any kind of thing. I still don't know of anything that really solves this perfectly, right? It would be satisfying, though, to have such a thing that was like log d minus 2 and still basically like n log d minus 1n or something like that for storage. But I think that's about it for today. I guess we probably have to go a little bit over time. So I think projects are still due, so I'd like to get, I think there's maybe a couple of people who still haven't sent me an email, but I'll go follow up with that later. All right.
What do they do?